Hi guys, welcome to today's lesson. So today we're going to be looking at geometry, but our main focus under geometry will be to introduce the deductive reasoning that we use in the geometry that we're going to be looking at. So in this lesson, we're going to be introducing the deductive reasoning, what it is all about, the reasons that we use whenever we are using the deductive reasoning, and some concepts under this geometry that we're going to be focusing on. So let's jump right into it. All right, so when we talk about the concept of Euclidean geometry, there are a lot of things that you're going to be considering, right? Mainly going to focus on the deductive reasoning, but there's also some theorems we're going to be throwing in there at a later stage to try and prove what we are talking about. But before that, let's talk about the origin of this Euclidean geometry that we are talking about. So there was a very intelligent gentleman called Euclid, who was a Greek mathematician who lived in the 4th century before Christ. So he is often called the founder of geometry, because really everything that has to do with geometry, he is the one who actually made all those theorems. Now, Euclid published a set of 23 definitions on which all of our theorems are based in, right? And that's where we're drawing all of this information we're going to try and talk about now. Euclid also used the definitions, the axioms, the theorems to create a deductive system which we use to solve all geometry problems that we have in maths. But now, the key terminology that you need to be familiar with is what an axiom is, right? So this will just be a rough statement. Rough statement, why am I calling it rough? Because we don't have any proof of what we are making a statement of, right? So this is a claim. In the universe, if I say A is equals to B, that is just a statement. I'm starting something that if I go to the theorem, which will be the process I'm going to use to try and prove this statement of mine, then what will that require? Will require the deductive reasoning that we're going to use. So we make a statement first, we undergo a certain process to try and prove that particular statement, and that process requires the deductive reasoning that Euclid was actually very interested in. So our main focus is this deductive reasoning. Now, before we can even talk about the deductive reasoning, because this is going to be coming up a lot of times, we need to first talk about what equality is, right? Equality would simply mean that things are same in value, right? Same in value. It can be an angle, it can be a distance, it can be a length, as long as one thing is equal to something else, meaning it is the same value as something else. That's what we're going to be talking about. Now, this deductive reasoning of ours, we start with the starting statement, right? I said this is our axiom, right? Because there is no proof that A is equals to B. Why? Because we don't know what A is. We also don't know what B is. But if we were to add the same amount on either side of this particular equality, then we know that the result will also be the same, right? Just a typical example, although I don't want you to be thinking numbers more than anything. If I had 20 degrees and 20 degrees there as my A and B, if I add the same number, 5 and 5 there, surely this is going to give me the same value on either side of the equal sign. So that's what we are trying to say here, that if I add the same amount to the inequality on either side, then the result will also be the same. Another thing would then be if I wanted to subtract now from both sides of the inequality, or of the equality, I mean, the result is also going to be equal. So, meaning if I subtract P on both sides, my result will still be the same. And you can even use numbers to try and prove this to yourself. If I have also certain lines being equal to other lines, right? AB, this is a length, is equals to PQ, that's a length as well. This is a length, that is a length. Then, when equal values are added, to or subtracted from this equality, the result is also equal. Now, guys, all of this that I'm trying to make you understand is, if I have a starting statement of claiming that two things are equal to each other, then if I add something else, right, but that something must be the same on either side, or subtract the same thing on either side from the initial thing that I said, this is equals to this, then it means my result will also be the same. So if I add 5 and 5, because initially this was equals to this and that will both have 5 added to it. And when I keep on saying this, I don't want us to mainly focus on numbers, guys, because then you're going to try and create numbers whenever you are trying to prove this using deductive reasoning. So please just don't try and look at numbers as yet. We are just looking at a line segment, an angle, another line segment, another angle, a certain constant that we are adding or subtracting. So that's what I want you to be focusing on mainly. Now, to show you what I'm talking about here, a plus b, right? So I am adding ab, rather, plus bc. And I know that ab, I was told that this is equals to pq. So it means this is the same as me having PQ plus, right? I was told that BC is equals to QR. So this will be PQ plus QR. Why? Because of the very first axiom that we had, which we always said is the starting statement. So as a result, this is what I will have. Now also, since I know what AB is, which is my PQ, I'm subtracting, right? Because this must link with that. I am subtracting BC, which I also know that this is QR. So it means this can be the same as PQ minus QR. And then that's how it will therefore become. All right, so one other example as well of this concept of deductive reasoning is, if I have A being equal to B, angle A that is, equal to angle B, and also angle A being equal to angle P, right? This can be in two different shapes, it can be in one shape, it does not really matter. This therefore simply means that B will also be equal to P, because both of them are equal to the angle A. As a result, angle B is equals to angle P. And that's how you can then look at the concept of deductive reasoning. Now, we also just try and throw in other examples of what we are talking about with the deductive reasoning. And I know that this might be a lot of letters and all of that we are trying to use. We're going to use this in terms of the reference to the questions that we're going to try and look at. If my starting statement is PQ is equals to QR, also I know that AB is equals to PQ and BC is equals to QR. It therefore means that AB is also equals to BC based on the initial statement that my PQ and QR need to be equal to each other. So is there any relationship between AB and BC? That's what you need to think about. And because I knew, right, that PQ was equals to QR, now I'm being told that this AB is equals to PQ, and this BC that I now have is equals to the QR that I originally knew. Then I can be able to answer this question of mine of whether there is a relationship between the AB and the BC. So as a result, that's what I will then say, that all of these line segments are equal to each other, all four of them, by the way. Now, as a result, you can deduce it to only being AB and BC. All right, so that's what deductive reasoning is all about. The concept of deductive reasoning is all about having a statement that is starting based on the statement, and I am now told other things, right? I go back to the statement as my basis of the whole argument I'm going to try and make, with these additional things that they throw in my way, and then I try and make a decision based on that. But remember, you cannot make a decision in mathematics or in geometry, to be specific, without giving me a reason. But what I want us to do now is to take a quick ad break. When I come back, I will then show you how we're going to apply all of this to try and solve questions that have to do with proving and solving for angles and lengths. But for now, please stay tuned. I'll be back just now. Hi guys, welcome back. I hope you are refreshed. So now we are going to try and apply all of what we've spoken about so far to proof, right? But first, we need to understand what this proof is all about. What do I mean when I ask you to prove something? And what do you need to do in order to write the proof, right? Let me repeat that again. What do I mean when I say prove something? And what must you do when writing the proof, right? So let me just show you what I'm talking about. Now, when you talk about proof, right? When a question says to you, prove that, the other word they normally use is also show that. This means that you need to give reasons why the statement is true, because the statement is true. Why the statement is true? Because the statement is true. It's not that I am saying you need to prove something and then the result might not be what I'm trying to say, right? The reason why the statement is true. And then for you to do that, this giving of reasons that I'm saying you need to do is therefore what we call the proof, right? So this will be the process that you write down. And the process will always be what? You having a statement, right? You give me a statement there. And then with the statement, you will therefore give me a reason why that statement is true, right, at all times. Not things like adding numbers or subtracting numbers. That's just basic algebra. But if you claim that angle A is equals to angle B, how do you know that? Why do you think that is the case if you were not told, right? If it was told in the statement, then you will always say my reason is given, right? But if it's because of a certain property that you know based on those two shapes you're talking about, you will also need to give me that reason and not write given there. So if I did not tell you that angle A is equals to angle B, you can use the statement, the reason given. You will need to tell me why you are making that claim, because this is a very big claim, by the way. I did say to you that an axiom is a baseless statement that we make that we're going to try and find reasons for in order to validate it. Now, if I am given in the sketch A, B, and C, D intersect at E, what does that mean? It means that these are straight lines, right? These are straight lines. And if these are straight lines, then you can consider things like vertically opposite angles, right? Because you can only talk about vertically opposite angles if the lines are straight opposite angles. You can also talk about adjacent angles on a straight line, which is just revision of things that you know, right? Adjacent angles on a straight line, right? You can only think about these things based on the fact that I'm telling you that A, B, and C, D are straight lines that are intersecting at E, right? So this is my A, B, and that is my C, D, right? Because at times you'll find that it's like that and it goes like that, where E is here and then my C is there and my D is there. This is not a straight line. Yes, DE is a straight line and CE is a straight line, but DC is not unless I make that statement there. So I hope that clarifies what I'm saying. Also, when I say to you AB, DB, and BC are drawn, I'm also still going back to that statement of mine to tell you that these are straight lines. EF is drawn, also a straight line, such that, or so that E1 is equals to A. So what do I know? E1 is this angle here. There, I'm told that it is equals to that angle there. And then also E2 is equals to C. So this angle here will be equals to that angle there. And then I am required to prove that E3, which is this angle, is equals to A plus C, right? Which is this one here plus that one there. Now, whenever we have this kind of a problem, we start by filling in the diagram, right? Filling in the diagram the information that you are given. So you can see I filled it in the previous question here where I was reading the statement. That's exactly what you need to do in your question paper or in your textbook if you are trying to do some homework. And then to apply all of this will then be the deductive reasoning that we are going to make, right? But now with this deductive reasoning of mine, what must be at the back of your head when you're trying to answer this question is, what is the relationship of A plus C, right? The two angles, if I add angle A and angle C, can I make a statement based on that and give it a reason why I think that statement is true? That's the whole point of deductive reasoning, guys, is to say, can I make a statement, which is my axiom, and with that statement, I must validate it by giving it a reason based on the properties that maybe I was told when the question was starting. And that's the whole point of deductive reasoning. So, with this one here, I must look at what angle A is, right? I was told that angle A is equals to angle E1, right? I was told that angle C is equals to angle E2, right? So as a result, this is the same as having angle E1 plus angle E2, right? And you know, the reason for this will be because I am given this statement based on the first thing that I said, right? So you can even start by first claiming that A is equals to E1, and then C is equals to E2, and your reason for that will be given. So this is what I really mean. Let me show you, because then you won't be drawing those errors for me there for a proof. So you will start by saying A is equals to E1, and you will say C is equals to E2. And both of these are because they were given on the statement, right? As a result, I know that A plus C will be equals to E1 plus E2, right? For this, I don't really need a reason because it's just the deductive reasoning that we are using. Then I can make a claim. Say, now I know that E1 plus E2 is equals to E3, right? And the reason for this will be because they are vertically opposite angles to one another. Now, do you understand what this means? Thus, which is what I want to now conclude, I will then say that A plus C is equals to E3, right? And you wouldn't really need a reason for that because it's part of the reasoning that we were talking about. Now, another type of a question that we have here will be, if they say sides HL and IH of a trapezium, right? Now, we need to look at the concept of a trapezium. What is a trapezium all about, right? One pair of parallel lines. That's what a trapezium does for us, right? So you therefore need to think about what? You need to think about the properties of parallel lines before you can even go anywhere. So you see, what I did was I just read the statement, Based on what I'm told on the statement, I'm now filling my head with some information that I must know already before I can talk about what the question wants me to do. So they are telling me this is a trapezium. Okay, what is special about a trapezium? We know a trapezium has one pair of opposite sides being parallel to one another, and then the other sides we don't really think much about them. So as a result, you can think about the properties of parallel lines, which is your corresponding, your alternate, and your co-inter. And that's how deductive reasoning works. You see, so it's not a thing that I must already know what all of these are all about. No. It is because of the little things that you are being told that you are going to apply here in order to try and solve this, right? So let's see how we are going to do that. So we know that we are told that H1 is equals to L1, and this is something that we are told in the statement, right? And we also told that LH is parallel to KI, which is one of the properties, or rather, which is the property of trapezium. So even if we're not really told that, we would know that those are the two parallel lines, since this is a trapezium. Now, to use this, we need to try and link K with something that will, at the end of the day, help us to locate K with I to be equal to each other. So what do I know from this diagram? I know that K is going to be equals to L1, right? So K will be equals to L1, and my reason for this will be alternate angles, but remember, you don't leave it there. They are alternate because GH is parallel to KI, right? Some people might not use GH, they might use LH. They both lie on the same line. That's just one line, so it does not really make much of a difference, right? So I know the statement. But from this, what also do I know? I know that L1 is equals to H1, right? But L1 is equals to H1. And what is my reason for this? I was told in the statement. Not that you must write I was told here, because you write given. And as a result, I will then say, I know that H1 is equals to I, because I'm trying to link the K with the I, and my reason for this will be, these are corresponding angles, but they are corresponding angles because GH is parallel to KI. Guys, if you don't indicate these parallel lines, then your reason will be incomplete. Then I can now say safely K is equals to I, right? And my reason for this will be because they are both equals to H1, which is what we initially spoke about. But you wouldn't really need to write that reason here, because you would have used the deductive reasoning of, I started with the first statement of I know this, alternate. I know this, I am given. I know this corresponding. If I link all of that, then I can claim what they want me to prove, and I will be done. So that's how you therefore use deductive reasoning to try and prove some questions in geometry. All right, guys, that's the end of what we have to do for now. We just need to take a quick ad break, and when we come back, we'll look at some more problems together. Please stay tuned. I'll be back just now. Hi guys, welcome back from the ad break. So we are still looking at the deductive reasoning that we undergo in terms of geometry, right? Euclidean geometry in particular. So now we're going to be focusing on the triangles, to try and now link triangles to this deductive reasoning. We say, how do I use deductive reasoning to talk about relationships between triangles. That's what we're going to try and do. So let's start by asking ourselves, what is a triangle? So, what is a triangle, right? As I said, a triangle, we know this is a closed 2D shape. Why 2D? Because this is a flat shape. That's what it simply means, right? 2D shape is a flat shape that is formed when 3 different line segments intersect at 3 different points. One line segment, let's call it A, B. Another line segment, let's call it B, C. Last line segment, let's call it A, C, right? And then what will we do? We will make all of these line segments to meet one another, right? To intersect and form this shape. So therefore it becomes, there's my A, there's my B there. Now I want the BC, so I'm starting at B, I'm going there, that is my C. I want my A and C, I'm starting at A, I go there, that is my AC. Voila, this becomes a triangle. And triangle, why? Because of the fact that we are talking about 3 sides, right? So as a result, this will have 3 sides and 3 angles as well, not necessarily equal to one another. It depends on what triangle you have. Now we have some classification on angles in terms of the types of the triangles that we have. We have what we call an acute angled triangle. This would mean the only angles you have in that are acute angles, right? The only angles you have are acute angles only, right, in that particular triangle. Then right-angled triangle, this one now does not necessarily mean, you see, my first description of what an acute angled triangle is, you don't really apply the same one here. It does not mean that there is 3 right-angled right angles in there. No, it just simply means that this has a 90-degree angle, right? 90-degree angle, right? Where one of the 2 segments meet, because remember they meet at 3 points. So one point of them must be at 90 degrees. And then with obtuse also we'll say at least one obtuse angle, at least one obtuse angle in that particular triangle angle. And then isosceles triangle, this then has some 2 properties that we need to look at. The first one is 2 equal sides, right? And we also have, because of that, 2 equal angles. And we actually start with equal angles because we're classifying it with angles, right? And then this will be the second point because of those angles being equal. Then the last one will be equilateral. Equilateral has 3 equal angles, and it also has 3 equal sides. See, so 3 equal angles and 3 equal sides. Now you can see my equal there looks very beautiful. Equal there, right? So 3 equal angles and 3 equal sides. Now let's see how we're going to try and apply all of these. You can see with this one here, let me just use a different color. This side is equals to that side, and that angle there will be equal to that angle there. So this will be considered the isosceles triangle that we have, right? And then let me just remove this. I'll just leave it as iso because then I won't have enough space. Then with this one, this angle, that angle, and that angle are all equal. As a result, this, that, and that will be equal. So this is therefore called the equilateral triangle, right? Now here you can see that I at least have one obtuse angle. This here is an obtuse angle in this particular triangle. So as a result, I will call this an obtused angle or an obtuse angled triangle. With this one, although it's not shown, I'm just showing you how we would see that it is a 90 degrees. It will be with that nice square of ours there, although mine looks like a rectangle. We normally show it as 90 degrees here. So as a result, this will be a right-angled triangle, right? Right-angled triangle. And then the last one will be, this is different from that, which is different from that. This is different from that, which is also different from that. So as a result, none of the angles are equal. We can call it a scalene. Remember, this is a scalene triangle, right? So we have isosceles, we have equilateral, we have obtuse, we have right-angled triangle, and then a scalene triangle can also be called the acute angled triangle. Acute angled triangle, not angles. So it's acute angled triangle. Now, to try and apply this, some parts of a triangle, we have what we call a vertex, right? So these are the points where the lines meet, the sides meet with one another, right? So my C there will be a vertex, A there will be a vertex, B there will be a vertex. D is not a vertex because it is just a point. It is not where two lines meet. It can only be a vertex if two lines are meeting at that particular point. We also have sides, which are the line segments that I told you about. Now, we have what we call interior angles. So you see where I highlighted with yellow. I am not necessarily saying that all these three angles are equal. No, I'm just showing you where the interior angles are. And based on these interior angles, the exterior angle, right, which will be this one, there are conditions for it to take place. One side must be produced, right? Now I will give you the meaning of what produced is. Produced means extended. In order for us to talk about an exterior angle of a triangle or even of a quadrilateral, which we're going to talk about at a later stage. But for it to be considered an exterior angle, one side, let me show you. Here's my side here. This side AC. Side AC is extended up until D there so that it becomes one straight line. Therefore, this will be considered the exterior angle of this particular triangle. If I was to extend that one, my exterior angle will be there. If I was to extend that one, it will be there. If I was to extend, it will be there, and all of that. So please just know it can only have an exterior angle if one side is extended. Now we also have the right-angled triangle. Now this one is a very special type of a triangle, right? Where we can use things like Pythagoras, right? Theorem. We can also use the trigonometric ratios, although we are not talking about that now, right? Trig ratios. So we can use all of this, but for now, because we are still under geometry, we are only going to focus on the Pythagoras. Now, the Pythagoras theorem here will say the square of the hypotenuse side is equals to the sum of the other two squares, right, added together. So this is the hypotenuse side, which is my longer side, squared. This is equals to AB squared plus CA squared, or AC squared. Now, we have what we call equiangular. Now, let's talk about this. Equi means equal, and then angular will mean angles, right? Equal angles. So if we're talking about equal angles, triangles, we're really talking about things that we can prove using similarity. And we need to just talk about the angles being equal, right? Because all corresponding angles must be equal. But you don't need to show all three of them. You can just show two angles to be equal. I promise you, the third one will be equal. So quickly, this is what I mean. If you say this is equals to that, and you say this is equals to that, automatically this will be equals to that there. So that's what I simply mean, right? You just need two. And as a result, corresponding sides will be in the same proportion. Then the last thing will be what we call congruency. Now with congruency, this has to do with identical triangles, where we then talking about equalness of this. But now with congruency, you don't need to prove all four theorems, right, or properties that I have. If you can prove one, I promise you, all the other ones are true, right? So if I can prove RHS, then all of this will be true. If I can prove SAS, which is side angle side, then all of the other things will be equal, right? So that's what we're trying to talk about there. So please make sure that you are clear on the properties of triangles and how we can use this. But when we come back, we're actually gonna use all of what I've spoken about so far in trying to then prove some similarities, or just to even talk about relationships of angles. Please stay tuned. I'll be back just now. Hi guys, welcome back. So as I said, we are going to apply all these properties that we've spoken about when it comes to triangles and the classification of triangles, and try to use those relationships in trying to prove certain things or certain relationships of angles. So let's just jump into it right away. So what I want you first to think about is we have what we call bisect a line, right? To bisect simply means to cut in half, right? So if I say that AB is bisected, I simply mean that at this point, which I will call M, it makes AM to be equals to MB, right? MB. That's what bisected means. And then bisect an angle also would simply mean the very same thing. It is to cut in half. But now what that means is if I have A, B, C, and I say that B is bisected, that will introduce something of this nature, right? Where this angle is equals to that angle because it is bisected, right? So that's what you need to think about, please. And then lastly, we have what we call bisectors. These will be the lines that cut the sides or angles in half. Right, so if I say this is an angle bisector, I'm saying that's a line that cuts those angles to be into two equal parts. Now, let's try and apply all of this that we've spoken about. If I say QR is parallel to ST, right, I'm not even going to continue with anything there because I'm now interested in what does this do for me on the diagram. Why is it important that I know that, right? What information will it introduce for me? What I know is this will introduce the fact that this is going to be equals to that there, and the reason for that will be alternate angles, right? And also, I will know that I can say this part here, which is W2, is equals to this part there, right, which is corresponding angles. I can talk about more things, right? I can talk about co-interior angles that I have, all of those things. I also know that I'm told WA and ZA are bisectors of QWZ and SZW. So let's start with the first one, Q. Let me just use a different color. QWZ, right? It makes this angle to be equal to that angle there. I'm going to show you in the next slide on a clean diagram. And then SZW will make this angle, right, to be equals to this angle. So I'm making it a cross and a dot so that it does not make it look like I'm saying all of them are now equal. Also, I know that I'm required to prove that A is equals to 90 degrees, which is this angle there. So let's talk about this. We feel what we are given on the diagram, and that's what I will know based on everything that I've spoken about. To use all of this now, I will then now say A plus Z, right, plus W5 is equals to 180 degrees. Let's quickly go there and find out why, right? This angle of A, that angle there, and this angle there. If I add all of them, they will give me 180 degrees. Why? Because it's interior angles of a triangle. So this will be interior angles of a triangle, right? Or rather, sum of angles in a triangle. And then now I want to try and talk about all of this and see, what do I now know? I know that W2 plus, oh, not W2, W1 rather, W1 plus W5 plus Z1 plus Z2, this is equals to 180 degrees. And this is because of co-interior angles. Why? Because I know that QR is parallel to ST, right? So as a result, I can equate these two. By saying that since they are both equal to 180, it means that A plus Z2 plus W5 will be equals to W1 plus W5 plus Z1 plus Z2. I hope you can follow everything that I am saying here, right? Let me just fix my Z so that you can see them clearly. This must be a Z. What else? That one, that one. So let me just write them properly for you. So that is a Z and that is a Z. So others are a bit clearer. Now, what do I know? Based on this, I know that there is Z2 there, there is Z2 there, there is W5 there, there is W5 there, right? Therefore, as a result, I will be left with A is equals to W1 plus Z1. Z1, right? But now going back to our diagram, what do we know? We know that W1 is the same as W1 is the same as W5. And we also know that Z1 is the same as Z2. So what that tells me is this will be A is equals to 180 degrees, right? Divided by 2. Because of the fact that Z1 is the same as Z2 and W5 is the same as W1. So I can then say I have 2 of that in order to make sure that I understand what I am trying to do here, right? So that's what I can then say, and that's how I can try and prove this. Now, one more example of how we can use all of this that we've spoken about so far. I am told that CD and BD are bisectors of the exterior angle ACE. That makes this to be equal to that. And then the interior angle ABC of the triangle ABC, right? So the interior angle ABC making this to be equals to that there. Please see that I'm trying to show them with different symbols so that they are equal. Now I'm required to prove that D is equals to half of A. But first, I add all the information that I know, and then I'm going to apply that by using the deductive reasoning. So now what do I know? I know that C3, right, C3 is equals to D plus B2, right? And this will be because it is an exterior angle of a triangle, right? And then I will say D is equals to C3 minus B2. And then also, what do I know? I know that C2 plus C3 is equals to A plus B1 plus B2, right? And this is also an exterior angle of a triangle. Based on that, I can then now claim that wherever I see my C3, I substitute it with D, right? With D plus B2, right? So this will be C2 plus, here it will be D plus B2, which is equals to A plus B1 plus B2. I just substituted there. And then B2 and B2, you know they're going to cancel there. And now what do I know? I know that based on this C and the A and the B, they must have a certain relationship with one another, right? And here's my C2 here. I'm trying to relate it to the angle A and the angle B1 there, right? So these two angles there, I'm trying to relate it to this angle C2 there. And as a result, that will make me to have D to be equals to A plus B1 plus a minus C2, I mean, minus C2, right? So if I minus C2 from A and B, that will only give me, and B1, that will only give me A alone and half of it, by the way. So therefore this will be D is equals to half of A, based on the fact that these two angles, if I was to subtract them, remember the deductive reasoning, if I subtract them from those two angles, it will be like half of that, which is this one here. And that's how I can then talk about these particular angles. All right, guys, we've come to the end of our show. I hope you've learned a lot, and I really, really have enjoyed doing this because geometry is so nice that you can visually see what you're talking about. But really, everything that is nice always needs to come to an end. I will see you guys next time. Remember, mathematics is food for the soul.